So I'm Stephen Hillion, and I'm co-founder and product lead at Alpine Data Labs, and DB Tsai is a senior research engineer focusing data science and machine learning at Netflix, and also a Spark contributor. DB's the star of the show. He did all the work on the functions that we're about to talk about. I'm sort of a consumer of those, and so I thought maybe the role that I can play is help to introduce sort of the motivation for some of the work that we did around these linear models. So I'll give a brief introduction to what we did and sort of the motivation. I'll talk about a little bit of the background around linear, nonlinear, non-parametric models, how feature engineering can help with making linear models more powerful, talk a little bit about regularization, and I'll hand over to DB, who will explain the implementation of the elastic net linear and logistic regression models that he built that's now part of Spark's, part of MLlib in 1.4. And he'll talk through how that was implemented and some of the benchmarks around that and how it compares to sort of state-of-the-art classification algorithms. So I don't think anybody would disagree that classification is a very important problem. It's a very common problem in government, business, research. Some classic examples of this are things like churn analysis, survival analysis, fraud detection. Even problems that have been attacked with other methods, like collaborative filtering for product recommendation, can themselves be recast into the world of classification models. And we see that, in some sense, for the average data scientist, something like logistic regression is sort of such a core and important part of the toolbox that I think while trends can come and go around some of the other classification algorithms, logistic regression especially is still a powerful method, and some of the research that has been done around this and some of the new implementations in Spark are particularly useful for people like me who work on large-scale data sets. Some of the classification problems I deal with, so for example, we're working on one right now for a large manufacturer that is focused on identifying and predicting machine failure. And what they will do is they create widgets that go, say, on the back of the car. One of the ones that we're looking at the moment is something that goes on the back of the car to do the beep, beep, beep noise as you back up. You don't want those to fail in the field, otherwise you get a small child being knocked over. So what they do is they look at the tests and the production quality data that comes for those widgets in their data sets, many hundreds of tests and different probes that are inserted alongside the manufacturing pipeline. And for those widgets that don't fail those tests but then fail later out in the field, they want to see if they could have predicted that within the factory. You've got then millions of widgets being produced every month. You've got tens of thousands of variables being tested as inputs into the potential failure. And so you've got big data in both senses, both wide and long. And often the relationships between the variables can be highly complex and in many cases nonlinear. So these days, kind of flavor of the month are algorithms like neural nets and random forest and SVMs, and those are very powerful, can get very high accuracy. But for me, as sort of a practitioner of data science, what I need above all, maybe even more than accuracy, are models that I can get into production quickly, that can be scored quickly, and that are interpretable. In many cases, the models that I want to build aren't actually going to go into production. I want to be able to glean business meaning from them. So I want models that are easy to interpret and that are fast to run, and that's often not the case for the non-parametric models, which, heuristically at least, can explode with the size of the data. So the solution that DB and the team have been working on tries to solve these problems with a couple of things. We use linear models, which are nice and simple and well known. We do automated feature generation, in particular with polynomial mappings that can expand the feature set but still keep it under control. And then use regularized regressions as a means of limiting the size of the data of the models eventually and making for more parsimonious and interpretable models. And also having some optimization techniques to say that even if your feature set does explode a little bit, we control for memory and so on so that it can run quickly in a framework like Spark. We actually use this as part of our product, so we regularly run very large regressions, as I was saying, certainly into the hundreds of millions and billions of rows and tens of thousands of variables. And we've able to be, the implementation that DB has worked on is so simple that we can wrap it up in a simple UI with a bunch of different parameters. It gets extremely high accuracy. We've used this most recently for a large telco consultant group that sells churn models to the big telco vendors, and very highly accurate churn models. We've used it there. And internal testing, we can definitely see that on sort of bulked up versions of data sets like MNIST, where you bulk it up to work on, say, hundreds of millions of rows, it runs in just a matter of minutes, and is very rapid indeed and conducive for sort of iterative modeling. So let's do a little bit of background, and then I'll hand over to DB. So first of all, linear, nonlinear. Many of you, of course, will be familiar with this already. So when you're trying to do classification in the sort of classic, say, logistic regression sense, or in simple SVM, you will have a line that you're drawing or a hyperplane that you're drawing between points, trying to find an optimal boundary separating red and green, true and false. But in many cases, the boundary in the solution space is, or rather in the feature space, is nonlinear and can be highly irregular, in fact. So the solution to this can be to use, say, non-parametric models that are good at gleaning the form of the model out from the data set itself, but, as I say, can be slow and difficult to interpret, either slow to train or slow to execute, perhaps more importantly. Or we can go with the approach that we've gone, which is to use linear models, but to bulk them up a little bit with feature generation. Feature generation, of course, is the real art of the data scientist, and I think that's sort of part of the philosophy behind this approach. Feature generation can be done manually when you know that log of income is probably more likely to be linear related to volume than just income alone, or it can be done in an automated way where you can apply different transformations and allow the coefficients of those transformations to be borne out by the training of the model. Quickly, some examples of linear models, of course, logistic regression, SVM, naive Bayes, LDA, and some nonlinear examples. Almost all of these, maybe with the exception of neural networks and non-parametric models, and all of these are, well, many of these are quite powerful, but again can yield models that are of the size that is sort of roughly proportional to the feature space, and therefore pretty unwieldy. The second ingredient in this talk is going to be around feature engineering, and to give a very simple case referring to these sort of nonlinear boundaries here, if you wanted to separate the red and the blues, that's not clear how to do that in this original two-dimensional space. You can't draw a simple line between these, but if you notice that the blues always have the same sign for their coordinates, and the reds have opposite signs, if you were to multiply two of the coordinates together to produce a second replacement substitute coordinate, you would get those being nicely separated by a line. So essentially your boundary then is sort of x1 times x2 equals a constant. So kind of like a rectangular hyperbola in the original space, and you can see how that would have worked in that space to give you a hyperbola that would have separated those. If you go back to that circle example, just x squared plus y squared equals a constant can lift up the space so that now you can separate, say, a circle of blue and red points with a simple hyperplane in that higher dimensional space. That maps down to a circle in the feature space, but again, just with a simple second order polynomial transformation, you're able to get this separation. So we've deliberately chosen sort of second order because what we found with a lot of the testing that we did was that second order, and also some of the research that's out there that DB will touch on in a second, is that second order polynomial expansions can work pretty well in terms of providing accurate models. Now you may say, well, I don't know ahead of time by looking at what that separation boundary should be, so how do I know what transformation to apply? But of course, if what you do is you throw in all the ingredients, all the possible second order summands into your in the training phase can actually find that out for itself. And the order of the size of the model then is going to be about order n squared, and if you think about kernel methods, the size of the model is getting to be sort of like n times the number of observations, which of course can be absolutely enormous. So the complexity, the dimensionality of the problem in this case can be really relatively quite small, sort of order n squared in the number of features n, or even smaller than that, because when the number of features is very large, typically that corresponds to problems where the training set is very sparse. And so it's really a sort of different order of magnitude in terms of the number of features that are going into the training of the model. So that can be a little bit of the strength about using these simple polynomial mappings as opposed to full kernel methods that you might use in something like SVM. And there's a nice theorem. I'm not really the scientist here, and so this seems either trivially obvious or highly complicated. This essentially says that if you map things into higher dimensional spaces, then you're more likely to be able to find that hyperplane and find a linearly separable way than in the low dimensional space. Well, that seems kind of clear to me, so I think I must be missing something. But anyway, it's good. The model during the training phase for incorporating too many features into the final model form. So there are a standard sort of way of doing this is to apply what's called Lasso Regularization, where you essentially take the absolute value of the coefficients and make that a penalization in your cost function when you're training the model. And that works pretty well, and because of the way the geometry works out, it essentially pushes as many of the coefficients down to 0 as it possibly can. So if you have variables that you don't really need in the model, that don't have a lot of weight in contributing to the model, they'll essentially get pushed down to 0, and so you have a very parsimonious model. You have just a relatively small number of variables that are going into the model. That's great. The problem with that is that sometimes you get rid of variables you actually don't want to get rid of. So if you have a model that has a lot of sort of grouped variables, like zip code, say, and you don't actually want to throw those out, they might be pretty collinear with one another, but you don't want to throw them out for the purposes of the final scoring of the model, then Lasso is not great. And then you might apply something like ridge regression, where it's going to push the coefficients down to 0, but not all the way to 0. So the idea between elastic net is it's sort of like trying to get the best of both worlds. It allows you to sort of shift the slider between the two forms of regularization, the L1 regularization, the Lasso, I'm getting those right? L1 is Lasso, I always get them wrong. The Lasso regularization on the one side and the ridge regression on the other. They both have pros and cons in terms of the performance of the model and its final accuracy and the efficiency of the model. What DB has done with this particular implementation is allow you to sort of essentially move that slider back and forth and see how it affects the accuracy of the model in the end. And that's what's known as the elastic net regularization. I cover that okay? Yeah. Okay, great. So with that sort of setup, that's just a sort of geometric interpretation, I'm going to let DB start talking about how we actually build this algorithm and how we build the optimization of this.
Okay, sounds good. Thank you for Stephen for the great introduction. So I'm going to quickly go through the intuitive interpretation of L1 and L2. So think about it, right? In L2, the penalization part of the weight is sum over all the square. So you can think about it, whenever you have a weight which is really large, okay, you penalize it more compared with L1, because you can think about it, the force gonna be the first derivative of the loss function, okay? So basically,